Let's begin our discussion with binary numbers. Now, when you hear the word bi, what do you think of? Bi is associated with the number 2. And so binary numbers have only two possibilities, 0 or 1. Now, when dealing with circuits, 0 is, or it corresponds to a circuit being in the off state. 1 corresponds to a circuit being in the on state. So if you're dealing with true and false statements, an off state will be considered false, and on state would be considered true. If you're dealing with voltage, an off state would have 0 volts, and an on state, typically 5 volts, but something other than 0. Now, before we go over and, or, and not gates, let's talk about the buffer gate. So here is the symbol of the buffer gate. And it basically looks like a triangle pointing towards the right. On the left, we have the input. On the right, we have the output. So we're going to call the input A. The output will also be the same. So if we were to make a truth table with the input and the output, if the input is on, which means it has a binary number of 1, the output will also be in the on state. If the input is in the off state, which means it has a binary of 0, the output will have the same binary number of 0 as well. Now let's draw a circuit to represent this. And the principal element of this circuit will be an NPN transistor. This is the base, this is the collector, and this is the emitter. Now we're going to connect this to a power source, and we're also going to use a light emitting diode. Now the light emitting diode, it's going to represent the output of the circuit. Now let's connect this to a voltage source. So here is the input, which we'll call it input A. And what's going to happen if we apply a voltage to point A? So if the input is in an on state, will the LED, will it be on or off? Well, once you apply a voltage to the base, the transistor will turn on. Current will flow from the collector to the emitter. Therefore, the LED will be in an on state. So this corresponds to a 1 for the input and the output. Now, what about if the input is off? So in this case, we have a 0 at the input. If there's no voltage at the base, then the transistor will be off. No current will be able to flow from the collector to the emitter. So therefore, the LED will be off as well. And so that's basically the buffer logic gate. So if you have a 1 in the input, you're going to have a 1 in the output. If you have a 0 in the input, you have a 0 in the output. Now the next type of logic gate that we're going to talk about is the NOT gate. So here is the electrical symbol for it. It looks like a buffer gate, but it has like a circle in the front. Now let's call the input A. The output will be the complementary of A. You can also write it as A bar. Now let's write a truth table. So we're going to have the input and the output. So if we have a 0 at the input, the output will be a 1. And if we have a 1 at the input, the output will be 0. It's always going to be the opposite. So basically, if the input is in an off state, the output will be in an on state, and vice versa. Now, how can we represent this using a transistor circuit? The circuit is going to be very similar to what we drew before, but there's going to be one key difference, and that is the location of the LED. So here is our voltage source, and on the left we have our input A, the emitter is attached to the ground, but the LED will be connected across the collector of the transistor and the emitter. So once again, this will be our output. So let's say if the circuit, or rather input A, is in the on state. Will the LED be in the on state or the off state? Well, let's analyze it. So once we apply a voltage to the base of the transistor, current will be able to flow from the collector to the emitter. So current will flow from the positive 5 volts through the resistor. Now, once it gets to this point, it has two options. The current can flow to the right or it can flow to the left. Now, electricity will always take the path of least resistance. And if the transistor is on, then the path of least resistance is from the collector to the emitter. So therefore, no current will flow in this direction. So this will be in the off state because the current has been diverted through the transistor. So notice that we have a complementary situation. The input is on, but the output is off. Likewise, the reverse is true. So let's say that the input is off. There's no voltage applied at input A. So what's going to happen? Current will still flow through the resistor. Now, once it reaches this point, because the transistor is off, it cannot flow through the transistor. So therefore, it has no choice but to flow through the LED. So therefore, the LED is in an on state. So as we can see here, if we have a 0 at A, the output will be a 1. And if we have a 1 at A, the output is a 0. And so that's the basic function of a NOT gate. It turns an off state into an on state and vice versa. It turns A into A prime. Now the next logic gate that we're going to talk about is the AND gate. And here is the symbol for an AND gate. We're going to have two inputs, A and B, and the output will be A times B. Now let's write a truth table. And at the same time, let's draw a circuit for this. So we're going to need two transistors as opposed to one. So this is input A and this is input B. And let's connect it to a voltage source. So what happens if input A and B are in an off state? Will the LED be on or off? In this case, both transistors will be off. So no current can flow from the positive 5 voltage source to the ground. So therefore, the output will be a 0 because the LED is off. Now, what if A is in an on state and B is in an off state? Will the LED be on or off? Current can flow through the resistor, through the LED, and through the first transistor. However, because the second transistor is off, no current can flow through it. So therefore, no current will flow through the LED. So the LED will be in an off state. So we're going to put a 0. The only way the LED can be on is if both inputs A and B are on. Only under that circumstance can current flow through the LED and through both transistors to make it to the ground. So thus we have the word AND. The only way the output can be in an on state is if both inputs A and B are on the on state. So even if B is on and A is off, no current will flow through the LED. Only if A and B are on. Now let's move on to the OR circuit. And let's begin by drawing the symbol for that. So here's how it looks like. So let's say this is input A and B. Now it's not going to be A times B as in the case of an AND circuit, but it's A plus B for the OR logic gate. Now let's make a table just like before. And let's draw a circuit that corresponds to it. So this time what we're going to have is two NPN transistors. But they're going to be connected parallel to each other to make the OR logic gate. In the case of an AND logic gate, they were connected in series with each other. And so that's the key difference between the AND and the OR logic gate. Now let's say that transistor A and B are in the off state. Will the LED be on or off? So clearly, no current can flow through the first transistor or through the second transistor. So therefore, no current will flow through the LED. The LED will be off. So we can put a 0 in the truth table. Now what about if the first transistor is on, but the second one is off? What's going to happen? Current can flow through the resistor, through the LED, but through the transistor that is on. So therefore, there's a path from the positive voltage source to the ground. So the LED will be on. So let's put a 1. Now what if transistor B is on, but transistor A is off? Current can still flow, but this time through transistor B. So the LED will be on. Now what if both transistors are on? In this case, the LED will definitely be on. Current can flow through transistor A or through transistor B. So thus we have the OR logic gate. The LED will be on if A or B is on. And so that helps me to remember the truth table for the OR logic gate. If we have a 1 in A or B, doesn't matter which one, the output will be on. Now I want to talk about the NAND gate, but let's compare it with the AND gate. The NAND gate is basically the complement of the AND gate. So here is the symbol for the AND gate. The NAND gate symbol looks very similar. The only difference is we're going to have a circle at the end. So let's say this is input A and this is input B. The output of an AND gate, we said it's A times B. For a NAND gate, it's going to be the complement of A times B. Now remember, the complement of a 0 is 1, and the complement of 1 is 0. Now let's look at the truth tables for these two types of gates. So as we recall, the only way to get a 1 with an AND gate is if both inputs A and B have a 1. Besides that, it will be a 0. In the case of a NAND gate, when both inputs A and B are on, the output will be off. So as you can see, this this column rather, is the complement of this column. Now we could use an AND gate and a NOT gate to construct a NAND gate. So here is the AND gate, and let's put a NOT gate next to it. So let's say this is input A, input B. The output of an AND gate is AB, and once you use a NOT gate, it basically takes the input and gives you the complement of that. So the complement of AB is just AB prime. And so the combination of these two logic gates will produce, or is equivalent to, a NAND gate. Now here's a question for you. Let's say if we have a NAND gate, and let's say if we take the two inputs of a NAND gate and connect them together. What type of logic gate do we now have? What would you say? So let's compare it to the original NAND gate. So this would be A and B, and we would get A times B, but the complement of that result. Well, now we only have one input because both of these will be A. And so if we multiply these two, it would be A times A, and then we'll get the complement of that. What is A times A? Now you need to be familiar with some rules of Boolean algebra, and we're going to go over those rules soon. But A times A is basically A. One way to help you to see this is if you multiply 0 and 0, you get 0. If you multiply 1 and 1, you get 1. Now keep in mind, we're dealing with binary numbers. And so in a binary system, it works out to be true. A times A is A. So this is the same as the complement of A. So notice that we went from A to A prime. This is the equivalent of a NOT gate. So that's how you could use a NAND gate to make a NOT gate. So these two are functionally equivalent. Now, let's understand how this works using a truth table. So let's write the truth table of a NAND gate. Now, once we connect the two inputs together, let's say once we make this circuit, here we have this circuit, by the way. These two columns has to be the same. So therefore, these two possibilities cannot work. Because let's say if this is A, this has to be A as well. So meaning, let's say if we have a 1, we can't have a 1 and a 0. That's not possible. It's either, if this is going to be a 1, both of these inputs will be a 1. Or if we have a 0 here, both inputs will be a 0. So these are the only two possibilities. So if we have a 0, the output is a 1. And if we have a 1, the output is a 0. And so this is the same table of a NOT gate. Now let's talk about the OR and the NOR gate. The NOR gate is the complement of the OR gate, much in the same way as the NAND gate is the complement of the AND gate. And so let's draw the symbols for both of these. The NOR gate looks like the OR gate, but with a circle at the end. So given inputs A and B, the output of the OR gate, we said it's A plus B. For the NOR gate, it's going to be A plus B, and then it's the complement of that result. Now let's write out the truth tables. the OR gate, the output of an OR gate, will be in the on state if either A or B is in the on state. Now, in the case of the NOR gate, it's simply the reverse. If either A or B is in the on state, the output will be in the off state. Now, one of the first things that you need to be able to do if you're taking a course in Intro to Logic Design is that you need to be able to write a function given a block diagram. So let's start with the first one in the upper left corner. The first thing I like to do is identify what type of logic gates I'm dealing with. So this is an AND gate. I'm going to use a capital A to represent it. Now, for over here, notice that the inputs of the first AND gate are A and B. And when dealing with an AND gate, you need to associate it with multiplication. And when dealing with an OR gate, associate it with addition. So what the AND gate is going to do is going to take the two inputs and basically multiply them together. So the output will be A times B. Now the second AND gate will take this input, which is AB, and multiply it by this input, which is C. So thus we could say that the output of this entire circuit, represented by function f, is going to be the product of A, B, and C. So this is the answer for the first one. Now what about the second one in the upper right corner? Feel free to pause the video if you want to try it yourself. So let's begin by identifying each logic gate in the circuit. So we have two AND gates, and here we have an OR gate. So the output of an AND gate is going to be basically the product of the inputs. So this is just going to be x times y, and here the inputs are x and y prime. So this is going to be x, y prime. Now the OR gate is going to take the two inputs and then it's going to add them together. So the output of the OR gate will give us the function xy plus the other input xy prime. And so we could say that function f is equal to xy plus xy prime. So that's how we can write the function using or given a block diagram. Now let's consider the third one on the bottom left. So this is an AND gate, and so is this one, and here we have an OR gate. So when dealing with an OR gate, we're going to take the two inputs and add them together. So this is going to be A plus B. And for the AND gate, we're going to take the two inputs and multiply them together. So this is A times B prime. Now here we have another AND gate, so we're going to take these two inputs, multiply them together. So we may need to use a set of parentheses. So the function is going to be A plus B, so that's this input, times A B prime. You could put that in parentheses if you want to, but you really don't need to. Now let's focus on the last one. We have one AND gate and two OR gates. So for the first OR gate, we're going to take the two inputs and add them together. So this is going to be x plus y. And for the second one, we're going to do the same thing. So this is going to be x prime plus z. Now for the AND gate, we're going to take these inputs and then multiply them together. So in parentheses, we have the first one, x plus y, and then times the second one, x prime plus z. So f is equal to what we have here. Now here is a challenge problem. Go ahead and write the function given the block diagram shown below. Feel free to take a minute and work on this one. So let's identify the logic gates that we have. So here we have an AND gate an OR gate, another AND gate, and then we also have an OR gate at the right. Now let's focus on the first AND gate. We're going to take the inputs x and y, and we're going to multiply them. Now for the OR gate, we are going to add xy with the other input z. So this will be xy plus z. Now for this AND gate, we are going to multiply these two together. So it's going to be x prime times xy plus z. Now, let's talk about the AND gate at the bottom. This is a 3-input AND gate. And the output of that AND gate is simply going to be the product of the 3 inputs. And so that's going to be x times y prime times z. Now the last thing we need to deal with is the OR gate. And this is a 3-input OR gate, and all we need to do is add the 3 inputs together. So anytime you're dealing with an OR gate, think of addition. When you're dealing with an AND gate, think of multiplication. So we could say the function f, the output of it, is going to be the first input, which is x prime times xy plus z, plus the second input, which is w, plus the last input, which is x, y prime, z. So this will give us the output of this circuit diagram using the inputs that we have here. So that's how you can write a function given a block diagram. Now let's work on the reverse. Let's say if we're given a function, how can we draw the block diagram? Let's say the function is ab plus c. Go ahead and draw the block diagram for that given function. So first, notice that a and b are multiplied to each other. So we're going to deal with an AND gate. And notice that we have an addition symbol. So we're going to use an OR gate between a, b, and c. So let's begin. Let's start with the AND gate. So here are the 2 inputs, a and b, and then the output of that will be just ab. Now we need to connect that with an OR gate. And then we need a new input, input c. So the OR gate will take the sum of these 2 inputs, and so we'll get the output ab plus c. And so that's it for that example. Here's another function. Let's say we have f is equal to xy plus x prime y plus y prime z. So go ahead and draw a block diagram for that given function. So notice that here we have what is called a product term. So we're going to use a AND function for this product term. Here this is another product term. So we're going to use another AND function to connect x prime with y. And we need another one to connect y prime with z. So we need 3 AND logic gates. Now we could use one OR gate to basically add the 3 AND logic gates together. Because we have the plus symbol or a sum, we need to use an OR gate. So this is going to be the first AND gate, and we're going to put x and y together, and so that will give us the output xy. And then we're going to use another AND gate, and we're going to have the inputs x prime y, and then another one. So this is going to be y prime and then z. Now we're going to feed these three AND gates into an OR gate. And so the output of the OR gate is going to be the sum of the three inputs. And so that's how we can draw a block diagram for this expression. Now, something else that you need to know. This expression here is something known as an SOP expression, which stands for sum of products. X, Y is a product, as mentioned before. X prime Y is a product, and Y prime Z is a product. So we have three product terms, and we're adding them. So that's a sum of products expression. Now, another term you need to be familiar with is literals. So every variable that you see, whether complemented or uncomplemented, is a literal. So X is a literal, Y is a literal, X prime is 1. So we have a total of 6 literals in this expression. Now let's consider another example. So let's say that F is going to be A plus B prime, and then times A plus B plus C times B prime plus C prime. Go ahead and draw a block diagram. Now the last example was a sum of products example. This one is known as a POS, which is product of sums. This right here is a single sum term. The reason why it's a sum term is because you're adding A and B prime. So notice that we have a total of 3 sum terms, and we're multiplying each of those 3 sum terms together. So thus it is a product of sums expression. Now, how many literals do we have in this problem? So we have 1, 2, 3, 4, 5, 6, 7. So there's a total of 7 literals in that expression. Now let's go ahead and draw the block diagram. Now, for a sum term, should we use an AND logic gate or an OR logic gate? What would you say? Now remember, you want to associate OR with addition or sums, and you want to associate AND with multiplication, or basically products. So because we have a sum term, we're going to use an OR logic gate for each one. So we're going to need 3 OR gates, and we're going to feed these 3 OR gates into a single AND gate because we do have multiplication here. So let's go ahead and draw the diagram. So let's start with our first OR gate. This is going to be a 2-input OR gate based on what we see here. So the first input is going to be A, the second one is going to be B prime, and the output of this OR gate will be A plus B prime. Now moving on to the second OR gate, it's going to be a 3-input OR gate. The inputs will be A, B, and C. The output is going to be A plus B plus C. And for the last OR gate, this is a 2-input OR gate with the inputs B prime and C prime. So this is going to be B prime plus C prime. Now let's feed these 3 OR gates into a single AND gate. So the output of this AND gate is going to be the sum, not the sum, but the product of these 3 expressions. And so you just got to multiply them. This is going to be everything that we see here. So I'm not going to write it again. And so this is the block diagram for the function f. Now let's work on number 3. Describe each of the following expressions as an SOP expression, sum of products, or POS expression, product of sums, both or neither. And at the same time, discuss the number of variables, literals, product terms, and sum terms, and identify any min or max terms. So let's start with this one. Let's say we have the expression x y prime plus x y z prime plus x prime y z w plus x y prime z prime. So is this a sum of products expression or a product of sum expressions? Or is it both or neither? So this is a product term. Each one of these are product terms. Now, just to review, one literal could be a product term. So x is a product term. Y prime is a product term. Or if you multiply them, these are product terms. So what we have here is a sum of products expression. We have 4 product terms, and as we can see, there's a plus sign separating them. So it's a sum of products expression. Now, how many different variables do we have in this expression? Notice that we have x, y, z, and let's not forget w. So we have a total of 4 different variables. Now, how many literals do we have? So here we have 2 literals. It could be complemented or uncomplemented. Here we have 3 literals. This has 4, and then this is 3. So if we add them together, there's a total of 12 literals in this expression. Now, what about if we have a min term or a max term? What would you say? In this case, since we're dealing with an SOP expression, a sum of product expression, we need to identify the standard product terms or the min terms. Now, a midterm is basically a standard product term that includes each variable of the problem. So it has to include all 4 variables, either complemented or uncomplemented. So this term right here is the min term in this expression because it has all 4 variables. Now let's move on to our next example. Consider this expression, x plus y times x prime plus z, and then times y plus z prime times x plus y plus z prime. So is this a sum of products expression or a product of sums expression? So x plus y, this is a sum term. X prime plus z is also a sum term. So notice that we have a total of 4 sum terms, and each of them are multiplied to each other. So this is going to be a product of sums expression. We have the product of 4 sum terms. Now, how many variables do we have in this expression? So I see 3 variables, x, y, and z. Now, how many literals are there in this expression? So here we have 2 literals in the first sum term. The second sum term has 2 literals, the third one has 2, and the last sum term has 3 literals. So thus we have a total of 9 literals in this problem. Now we're not going to have any min terms because this is not a sum of product expressions. But we do have a max term because this is a product of sums expression. So what is the max term in this particular problem? So which sum term includes each variable of the problem, either complemented or uncomplemented? So this is the sum term that has all the variables. So therefore this is considered the max term. Now let's move on to our next example. Let's say we have the expression x, y prime, z, w. So this expression, is it an SOP expression, a POS expression, both, or neither? What would you say? It turns out that this is both a sum of products expression, and you could describe it as a product of sums expression. So in terms of, let's say, SOP, we could say that this is the sum of one product term. Now, in the case of a POS expression, you can also describe it as the product of 4 sum terms. Now, if that statement confuses you, see it this way. X, you could think of x as x plus 0. Y prime, you could see it as y prime plus 0. And then z plus 0 and w plus 0. Now, in this form, it looks more like a product of 4 sum terms. At least that's one way I think of it. But that particular expression can be described as both a SOP and a POS expression. Now, how many variables do we have? And how many literals? So for this expression, we have a total of 4 variables: w, x, y, and z. We also have 4 literals: w, x, y prime, and z. So that's all we could say about this expression. Let's move on to our next example. Consider the expression a plus b plus c prime plus d plus e prime. So can we describe this as an SOP or POS expression? Like the other example, you could represent it as both POS and SOP. So as an SOP expression, we can say that this represents the sum of 5 product terms. And as a POS expression, we could say that this represents the product of 1 sum term. So imagine if we put it inside a single set of parentheses. In this case, this would appear as 1 sum term. Now, it's important to understand that if you have just 1 literal, let's say it's either x or y prime, 1 literal can be considered a product term or a sum term. So just keep that in mind. Now for this particular example, we have a total of 5 literals: a, b, c prime, d, and e prime. We also have 5 variables: a, b, c, d, and e. And so that's it for that expression. So make sure that you understand the difference between a product term, a sum term, and a literal. So a product term could be just a single variable x, it could be y prime, or it could be multiple literals multiplied to each other, like xy prime or xyz. So those are product terms. A sum term can be an individual literal. It could be x, it could be z prime, or it could be a sum of multiple literals like x plus y, or even x plus y prime plus z. So those are sum terms. And a literal is just a variable. It could be x, y prime, it could be complemented or uncomplemented. So that's a literal. Now let's consider one more expression. Let's say we have a multiplied to b plus c d prime. What type of expression do we have? So here we have a single term, like a literal, and this is a product term. And it looks like just a mixture of SOP and POS. It turns out that this expression is neither. It's neither a sum of products or a product of sums expression. Now, this expression has 4 variables. As we can see, it's A, B, C, and D, and it has 4 literals. If we list them, it's A, B, C, and D prime. And that's all we can say about this expression. So this is an example of an expression that is neither SOP or POS. Now let's say if C wasn't there. What type of expression will we have now? Would you still say it's neither? Because this is now a sum term. When you have C here, this is no longer a sum term. But when you take away C, now we have a sum term. And A is considered a sum term. You can write that as A plus 0. So that's a sum term. And then B plus D prime. That's another sum term. So this is the product of 2 sum terms. So this would be a POS expression. But once you put C into the mix, this is no longer a sum term, nor is it a product term. So this would be neither. Now let's review some basic rules of Boolean algebra. Now whenever you see a plus sign, know that you're dealing with the OR logic gate. And if you see like multiplication or a product term, remember you're dealing with the AND logic gate. So the first law that we're going to go over is the commutative property. A plus B is the same as B plus A. And A times B is the same as B times A. The next one is the associative property. So A plus B plus C is the same as A plus B plus C. And A times BC is the same as AB times C. So that's the associative property. And as you can see, the order for the and or operators doesn't matter. The next one is the identity rule. A plus 0 is equal to A. And A times 1 is also equal to A. The next one is the null property. A plus 1 is equal to 1, and A times 0 rather, is equal to 0. Now, if you're analyzing this using old school algebra, this equation might make sense to you, but this one might be a little confusing. For instance, if a is 0, 0 plus 1 equals 1. Okay, that makes sense. But what if a is 1? 1 plus 1, does it really equal 1? Well, in old school algebra, 1 plus 1 is 2. But when dealing with Boolean algebra, 1 plus 1 does equal 1. And let's prove that using logic gates. So here we're dealing with the OR logic gate. So let's draw that. Now we're going to have two inputs, A and B. But B, we're going to say is always equal to 1. Now the output will be A plus B. Now let's make a truth table. Now remember, the output will be a 1 if either input A or input B is in the on state. So A could be 1 or 0. B is always 1. So this is B. So if A and B are both in the on state, then this logic gate will be on. So we're going to give it a value of 1. Here, B is on, A is off. So if one of the inputs is on, for the OR gate, the output will be on. So in this case, if A and B are in the on state, we can see that the output is 1. Here, if B is on, A is off, the output is still 1. But this is the one that we're working with. So 1 plus 1 does equal 1 when dealing with logic gates. This means that if A is on and B is on, then the output, A plus B, will be on as well. And that's the way you have to think about it when dealing with these types of Boolean algebra expressions. Now the next rule that we're going to talk about is the complements. A plus A prime is going to be 1. And A times A prime will always be 0. So this is the complement property. Now, using numbers, if you have a 0 and a 1, let's say if A is 0, A prime has to be 1. This is going to be 1. So when dealing with the OR logic gate, if one of the inputs is in the off state and the other is in the on state, the output will be on. So that's what 0 plus 1 equals 1 mean. Now, for this one, we're dealing with the AND gate. So let's draw that circuit. So let's say if we'll call this A and A prime. So if A is on, that means the other one, A prime, will be off. Now, when dealing with the AND logic gate, the only way the output will be on is if both inputs, A and B, or in this case, A and A prime, are both on, because keyword AND. Well, this will never happen, because if A is on, A prime will automatically be off. So the two inputs will never be on at the same time. So no matter what, this is always in the off state. So we're going to have a binary number of 0. Therefore, whenever you use an AND logic gate with the A and A prime inputs, the output will always be 0. It will always be off. Now let's move on to our next operation. Idempotency. I believe that's how you say it. So for this particular property, you need to know that A plus A is equal to A, and A times A is equal to A. So 0 plus 0 is equal to 0. So if you have an OR logic gate, if both inputs are off, the output will be off. And also 1 plus 1 is equal to 1. So if both inputs are in the on state, the output will be on as well. Now, when dealing with an AND logic gate, 0 times 0 is 0. So if both inputs are off, the output is off. And 1 times 1 is 1. If both inputs are on, the output is on. So let's think about what we can do with this. So when dealing with Boolean algebra, we could take a variable a and replace it with a plus a. In fact, we can take the variable, let's use a different variable, x, and replace it with x plus x plus x. If you want to, you can add another x, because this is equal to x, this is equal to x, this whole thing is equal to x. It doesn't matter. If all four of these are in the on state, then this one will be in the on state as well. Now for the next one, it's going to be called involution. And this one is pretty straightforward. If you take the complement of A, you're going to get A. It's like a double reverse. So the complement of 0 is 1, and the complement of 1 is 0. So that's the involution property. The next one is the distributive property. So for the OR operation, A times B plus C is equal to AB plus AC. And using the old school algebra, this makes sense. A times B gives you AB, and then A times C gives you AC. No issues with that one. Now, for the other side, it looks like this. A plus BC is equal to A plus B times A plus C. Now, this one might look a little weird. You might be wondering, like, how does that work? Let's prove this using a truth table. So we have three inputs, A, B, and C, each with two states, on or off, 0 or 1. So how many combinations can be made with three variables with two states? So this is going to be 2 to the third power, so we have 8 possibilities. The first possibility is that we have all zeros. The second is 0, 0, 1. The third is 0, 1, 0. And then 0, 1, 1, 1, 0, 0, 1, 0, 1, 1, 1, 0. And the last one is 1, 1, 1. So we have 8 different combinations. Now, let's focus on the left side. So the next column that we need will be BC. And then it's going to be A plus BC. That line is not straight. Now, something else that I want to write, which I'm going to have to delete soon, so you may want to write this down. When dealing with operations, particularly the OR operation, know that 0 plus 1 is 1, and 1 plus 1 is 1, but 0 plus 0 is 0. And you could prove that using the OR logic gate. Now for the AND logic gate, 0 times 0 is 0, 0 times 1 is 0, and 1 times 1 is 1. So that makes sense. The only one that you may have to keep in mind is that 1 plus 1 is 1 in Boolean algebra. So knowing that will help us to complete this table. So B times C, 0 times 0 will give us a 0. 0 times 1 is 0. 1 times 0 is 0. 1 times 1 is 1. Here we have 0 times 0, and then 0 times 1, and then 1 times 0, and then 1 times 1 is 1. Now for this one, we are going to add A and BC. So 0 plus 0 is 0. Here we have 0 plus 0 again, and then the next row is the same. Next is 0 plus 1, which is 1, and then 1 plus 0, that's also 1. And then you can repeat the process. The last one is 1 plus 1, which is 1. So that covers the left side of the equation. So we're going to pay attention to this column because that's the total value of the left side. Now let's move on to the right side. So let's start with a plus b. And then we're going to have a column for a plus c. And then the last column will be a plus b times a plus c. And so this is going to be the right-hand side. Our goal is to prove that the left-hand side is congruent to the right-hand side. If they're the same, then we've proven that this property is true using the truth table. So now let's add a and b. So 0 plus 0 is 0. And then we have the same thing again. 0 plus 1 is 1. Same thing here. And then 1 plus 0 is 1. And 1 plus 1 is 1. Now let's move on to the next one, a plus c. So we have 0 plus 0, which is 0. And then it's 0 plus 1, which is 1. And then 0 plus 0, that's 0 again. Next we have 0 plus 1, 1 plus 0, 1 plus 1 is 1, and then 1 plus 0 and 1 plus 1. Now, a plus b times a plus c. So what we're going to do now is we're going to take these two columns and multiply them together. 0 times 0 is 0. 0 times 1 is 0. And 1 times 0 is 0 as well. And then the rest is just 1 times 1, which will be 1. Now our next step is to compare these two columns. Are they the same? And we can clearly see that they are, which means mathematically in Boolean algebra, this expression is correct. And so that's how you can prove a mathematical statement in Boolean algebra using a truth table. Now we can also prove it algebraically. Now going back to this expression, let's say if we're given the information on the left and we go to the right, that process is distribution. The reverse is known as factoring. So if we started with the right side, notice that we have a common factor, a. So if we factor out a, we can get b plus c. And we're going to use that often. So let's see if we can mathematically prove that statement without a truth table. So I'm going to start with the right side of that equation. A plus b times a plus c. And let's FOIL. So here we have a times a, which will give us AA, and then a times c, so that's AC, and then this is going to be b times a, and then b times c. Now I'm not going to touch b times c because I want to keep that, so let's leave that alone. What is a times a? Now if you go back to the rules we talked about, I believe this one is, it's the, not the complement, but which one was that? I know I saw it before. It was the idempotency rule. If you go back to that one, then it says that a times a is a. 0 times 0 is 0. 1 times 1 is 1. So using the idempotency rule, we can convert a times a to a. So we have a plus ac plus, I'll write that as ab. And we could use, that was the commutative rule. AB and BA is the same. Now, what I'm going to do is I'm going to factor out an a. So this is going to be a times 1 plus c. Now let's focus on this, 1 plus c. There's a property that we talked about early in this video that we can use here right now. Do you know what it is? If you don't, pause the video and look through the properties that we discuss and find out what we can do. The property that you want to use is the null property. If you recall, we said that a plus 1 is a, or 1 plus a is a. So therefore, 1 plus c is c. Now, if you ever forget the properties, sometimes you can just plug in numbers to see what's going to happen. So, does the value of c really matter? So let's say if c is 0, 1 plus 0 is still 1. What if c is 1? 1 plus 1 is still 1. So 1 plus c will always be equal to 1. So the value of c does not matter in this expression. So we could just replace 1 plus c with 1. And so we have a plus ab plus bc. Now a times 1, or 1 times a, is still a. Now notice that what we did here, we can repeat that here. So let's factor out an a. So this is going to be a times 1 plus b plus bc. And just as 1 plus c was 1, 1 plus b is 1. So we're going to have a times 1 plus bc, and then that's the same as a plus bc. So that's how we can prove that a plus b times a plus c is a plus bc, in addition to using the truth table method. Consider the function f, which is x y prime z plus xyz plus x prime y z plus x prime y z prime, and then plus x prime y prime z. Now this function will require, let's say if we were to draw a block diagram, it's going to require at least 5 AND gates. And each of those AND gates need 3 inputs. And we definitely need an OR gate that has 5 inputs, or you could break it down into multiple OR gates. So to design a circuit, it's going to be very complex. But using Boolean algebra, is there any way in which we could simplify this function so that we can still get the same desired result while using less circuit parts? So how can we simplify this function? Because right now, what we have is a sum of products expression with 5 product terms and 15 literals. We want to simplify the function to reduce the number of product terms and literals if possible. So what can we do using the algebraic rules that we've just considered? The first course of action that I would recommend is to factor. In the first 2 terms, we can take out the x and the z variable, and so we'll be left with y prime plus y. Now, in the next 2 terms, notice what we can take out. We can factor out x prime and y, leaving behind z plus z prime. Now, we can employ the complement property, which states that a plus a prime is 1. So y plus y prime is going to be 1. And z plus z prime is 1. So thus we have our answer. The function is equivalent to xz plus x prime y plus x prime yz. So now we only have 3 product terms with 7 literals. And so the function has been simplified. But now, is this the furthest we can go? Can we simplify it any further than what we have here? It turns out we can. Notice what we can do. We can factor out in these two terms x prime y, and we're going to have 1 plus z. And so using the null property, we know that 1 plus z is just 1. So this is going to be xz plus x prime y. So now it's fully simplified. But is it really? Can we simplify it further? Right now, we have a very simplified function. We still have a sum of products expression with 2 product terms, 4 literals, and 3 different variables. But let's see if we can do something else. Let's see if there's another way in which we could simplify it. Now, I'm going to focus on this term. If you recall, there's something called the idempotency property, which says that A is equivalent to A plus A. So that means that we can take a variable and basically copy it in an equation, and it will still be true in Boolean algebra. So x prime yz, we can replace that with x prime yz plus another x prime yz. Now sometimes it makes sense to introduce another term, like copy it, because if you do that, it turns out you can simplify the function even further. And that's what we're going to do in this example. So I'm going to copy that expression. But I'm going to write it next to this one. And I am running out of space. So as you can see, here is the extra copy. Now let's see what's going to happen. So let's factor out the GCF in those two terms. So f is going to be x z times y prime plus y. Now let's take out the greatest common factor in those two terms. So that's going to be x prime y. And we're going to be left with z plus z prime. Now let's do the same for the last two terms. We can take out an x prime and a y variable. So we'll be left with z plus z prime. And I almost made a big mistake. And that is that this is not y but y prime, as we can see here. So y and y prime are different. I can take out a z. So we can take out x prime z, and we're going to be left with y plus y prime. So using the complement rule, y prime plus y is 1. And the same is true for z plus z prime. So now the function is going to be xz plus x prime y plus x prime z. Now, what do you think we can do at this point? What do you recommend that we should do right now? So let's focus on these two terms. Notice that we can take out a z variable. So we're going to have x plus x prime, and then we're going to be left over with x prime y. So x plus x prime is 1. So our final answer is z plus x prime y. So now we have a total of 3 literals as opposed to 4 literals. So sometimes you may need to use the idempotency rule to add another term so that you can simplify the function even more, which is what we did here. Now, there's some more rules of Boolean algebra that you need to be aware of. So let's write the two columns that we had before. The next rule that we're going to talk about is something called the adjacency rule. And here's the formula. AB plus AB prime is equal to A. And the other one, it goes like this. A plus B times A plus B prime is equal to A. Using the rules that you already know, go ahead and prove that those equations are true. So on the left, what we could do is factor out an A. And so we're going to have B plus B prime. I'm going to keep the right side the same. Now using the complement rule, we know that B plus B prime is 1. And A times 1 is A. So this holds true. Now for the second one, we could FOIL. So we have A times A, which is AA, and then A times B prime, and then B times A, which we can write that as AB, and finally, B times B prime. Now we know that A times A is A, based on the idempotency rule. And here, these two terms, we can factor out an A, giving us B prime plus B. Now what is B times B prime? So this is the complement rule for the AND operation, or multiplication. And if you're not sure, or if you forget, plug in a number for B. Let's say if B is 0, B prime has to be 1. 0 times 1 is 0. Or if B is 1, B prime has to be 0, so it's still 0. So no matter how you analyze it, a variable times its complement will always equal 0. And so that is the complement property of multiplication, or for the AND operation. Now we can use the complement property that's associated with addition, or the OR operation. We know that B prime plus B is 1. And so right now we have A plus A left over. And using the idempotency rule for addition, A plus A is A. So that's how we can prove that the adjacency rule is true using the other rules. Now let's move on to the simplification property. So here's the first one. A plus A prime B, all of that is simply equal to A plus B. And the other one is A times A prime plus B is equal to AB. So how can we prove that? Well, the one on the right is not that bad. If you distribute, you get A times A prime. And then here you get plus AB. Now, using the complement rule, we know that A times A prime is 0. So we can see that AB is equal to AB. Now, what about the one on the left? So I want you to pause the video and prove that this equation is true using a truth table and using Boolean algebra. Go ahead and take a minute to work on that. So we have two variables, A and B, with two possible states, on or off, 1 or 0. So we have four combinations, 0, 0, 0, 1, 1, 0, and 1, 1. Now for the right side, it's A plus B. So let's put that in red. Now for the left side, we need the complement of A, which we could see here. And then we have a product term, A prime B. And then we're going to add A to that. So the last one is going to be A plus A prime B. And this is going to be the left-hand side of this equation. Now let's go ahead and fill out the table. So let's start with this one, a plus b. 0 plus 0 is 0. 0 plus 1 is 1. 1 plus 0 is 1. And 1 plus 1 in Boolean algebra is 1. Now the complement of a, all we need to do is basically put the other number for that column. So if you see a 0, put a 1. If you see a 1, put a 0. Now we're going to multiply a prime by b. So 0 times 1 is 0, and 1 times 1 is 1. Next we have 0 times 0, so that's 0. And finally 1 times 0 is 0. Now the last thing we need to do is add the first column with this column. So 0 plus 0 is 0, and then 0 plus 1, so that's going to be 1, and then we have 1 plus 0, which is 1, and the same is true here. Now our last step is to compare the data on the right hand side with that on the left hand side. So we can see that they're the same, which means that this equation is true. So now let's prove it using algebra. What rules can we use to algebraically prove that this equation is true? You want to use the distributive property for the AND operation. Recall this one, a plus bc is equal to a plus b. Well, let me show you how you can set it up first. So start with this letter. It's going to be a, and then it's plus b in the first parentheses, and then plus c in the second parentheses. So we're going to follow that same setup. Starting with the left side of this equation, we have a plus a prime b. So the first letter is a, which is going to be on the left side of both parentheses. Next we have a prime, that's only going to be in the first one, and then b, which is going to be in the second one. So now let's focus on simplifying the right side. So here we have a plus its complement. So using the complement rule for addition, a plus a prime is basically just 1. It's always going to be 1. And then times a plus b, that's simply equal to a plus b. And so that's how we can algebraically prove that this equation is true. You can see that these two are the same. Using what you've learned thus far, go ahead and simplify this function. Feel free to work on that. Now, what I'm going to do in this example is I'm going to focus on the last two terms, since I can take out the a variable. And if I do that, I'm going to have b prime plus bc. Now, what can we do here? What we can do is we can not factor, but we can use the distributive property for the AND operation, just like we did before in the last proof. So we're going to start with this variable, b prime, and we're going to write it in both parentheses. Next, we're going to write this one in the first one, plus b, and then this one in the second one. So that's how you can employ the distributive property for the AND operation. So now let's simplify it. B prime plus B, we know that's B1. So now we could distribute the A. So A times B prime, and then A times C. So as you can see, the function has been slightly reduced from what we started with. Before, we had a total of 7 literals. Now we have a total of 6 literals. Now let's move on to something called De Morgan's theorem. If we take the complement of the sum of two variables, let's say a and b, we are going to get the product of their complements. Likewise, if we take the complement of the product of two variables, we are going to get the sum of their complements. So notice that here we have a sum term and it's being converted into a product term. Here we have a product term and it's changing into a sum term. Now you can expand De Morgan's theorem for additional variables. So look at this equation. Instead of a plus b prime, we could say a plus b plus c prime, and that's going to be equal to a prime, b prime, c prime. Likewise, on the right side, if we have a, b, c prime, then that's going to equal a prime plus b prime plus c prime, and so forth. So you can add d, e, f, you can expand it as far as you want to. Number 4, use De Morgan's theorem to find the complement of the given function shown below. So the complement of f is basically just f prime. So what we're going to do now is we're going to rewrite the function, but within a set of parentheses. And then we're going to write the complement symbol outside of that parentheses. Now notice that we have a sum of products expression. And once you find the complement, you're going to get a product of sums expression. So for now, this is the formula we need to use. A plus b plus c prime. All of this is equal to a prime, b prime, c prime. And if you want to, you can put this in parentheses. So notice that a corresponds to xy, b corresponds to x prime yz, and this corresponds to c. So here we're going to have a in parentheses, which is xy, and then prime, and then b, which is x prime yz, and then c, which is w y x prime. So notice that we converted the addition symbols to multiplication symbols after we distributed the complement to each product term. And I think I forgot to put a prime symbol there, so let me go ahead and do that now. Now what's our next step? So starting from this point, we need to use another formula. So let's use this one. AB prime is equal to A prime plus B prime. So here we have XY prime. So that's going to be X prime plus Y prime. So notice that we need to distribute this complement symbol to X and Y. In order to distribute it to X and Y, we got to change the multiplication that's between them into addition. So let's go ahead and replace this with X prime plus Y prime. Now let's move on to the second part. And that's this part. So we have three variables. And so we're going to use this expression. A, B, C prime is equal to A prime plus B prime plus C prime. So therefore, X prime YZ prime is going to be equal to X plus Y prime plus Z prime. So let's write that here. X plus Y prime plus Z prime. Now for the last one, now that we know the process, we could just write it in. So we're going to distribute the complement symbol turning the multiplication sign in between them into addition. So w will become w prime and then plus. Y is going to change to y prime. X prime will change to x. And that's it. So this here is the complement of this function. So here we have a sum of products expression, and now we have a product of sums expression. So that's how you could use De Morgan's theorem to go from an SOP expression into a POS expression. Now let's show that our work is correct by going in the reverse order. So we have that f prime is basically x prime plus y prime times x plus y prime plus z prime, and then times w prime plus y prime plus x. So let's use De Morgan's theorem on this expression to get back the original function xy plus x prime yz plus w y x prime. Now there's two ways that we could do this. So going back to the last problem, we went from f to f prime. Let's call it path A. Now granted, we could take the same route back to f and get the answer. But we don't want to do that. Instead, let's take a different path. We'll call it path B to get back to our original expression. And so what we're going to do to get f is we're going to take the complement of f prime. So we could say that f is basically f prime prime, which I believe is the involution property. So let's use that. So let's write f prime within a set of brackets. So let's begin by distributing the complement symbol. Now, as we distribute the complement symbol to basically the three sum terms, not product terms. As we distribute it to the three sum terms, the AND operation that we see between them will change into an OR operation. So you could think of multiplication being converted to addition. So let's apply to the first one. So we have x prime plus y prime, and here is the complement symbol that we've applied to this one. Notice that we just put it outside of the parentheses. We haven't touched anything inside the parentheses yet. Now the multiplication between these two sum terms will now change to addition. Now let's apply it to the second parentheses. So this is going to be x plus y prime. Don't change anything on the inside. And then let's put the complement symbol outside of that. Now let's change multiplication to addition. And then do the same thing. W prime plus y prime plus x with the complement symbol outside of that. Now let's apply the complement symbol to the variables on the inside. Now keep in mind, as we do so, the OR operation will be converted to an AND operation. So we're going to convert the addition symbol into a multiplication symbol. So x prime will be converted to x, y prime will be converted to y, and we're going to put them together to indicate the AND operation. Now we're still going to have this positive or this plus symbol because the complement will not affect it in this case. It's outside of the parentheses. It's only going to affect the stuff that are inside the parentheses. So now let's apply the complement symbol to all of these three variables. So it's going to be x prime and then times y times z. And then plus, let's do the same for the last one. So distribute the complement symbol and change the AND operation into, the OR operation into an AND operation. So it's w, y, x prime. And so this is the original function f. So we've went from a product of sums expression back to a sum of products expression. Now let's work on a different example. So let's say if we have the function g and it's equal to x prime plus y prime times x plus y prime plus z prime, and then w prime plus y prime plus x. So what I want you to do is, using De Morgan's theorem, find the complement. And once you find a complement, take the complement of that to get the original function. So feel free to pause the video and try that example. So let's begin by rewriting this function. And let's take the complement of it. So the type of function that we have right now is, would you say this is a sum of products or a product of sums? So these are sum terms, and we're multiplying them. So this is considered a product of sums expression. So let's convert it to a sum of products expression. So just like before, the first thing we're going to do is apply the complement to the three sum terms, changing the AND operation into an OR operation. So we're going to have x prime plus y prime, and then prime, and then this is going to be plus, and then it's going to be x. Don't change anything on the inside right now. That's going to come later. And then we're going to have prime and plus, and finally w prime plus y prime plus x with another complement symbol. Now we really don't need the bracket symbol here. We could take it out at this point. Now the next thing that we need to do is that we need to distribute the complement symbol to the variables inside the parentheses. So the OR operation, indicated by the plus sign, will be converted to an AND operation, which will be indicated by multiplication. So x prime and y prime will change to x, y, and we're going to multiply them together. So we could just write it as xy. Now, this plus is unaffected. It's outside of the parentheses, so it's not affected by these complement symbols. Now, let's move on to the next one. So x will be changed to x prime, y prime will be changed to y, z prime will be changed to z. And the plus symbols inside the parentheses will be converted to multiplication. So this is going to be x prime, y, z, and then plus. Let's do the same for the last one. So w prime becomes w times y prime becomes y, the plus sign becomes multiplication, and x becomes x prime. So now we've converted a POS expression into a SOP expression, a sum of products. We have the sum of three product terms. So now what we're going to do is we're going to try to go backwards. To get g, we are going to take the complement of g prime. So let's write xy plus x prime yz plus w y x prime, all within a bracket, and let's put the complement symbol outside of that. So what do you recommend that we should do in this case? What I recommend before distributing the complement symbol is to take each product term and put it in parentheses. Now, let's distribute the complement symbol to each parentheses that's inside the bracket symbol. So we're going to have G is equal to, now as we distribute the complement symbol, the OR operation inside the brackets will be converted to an AND operation. So basically addition becomes multiplication. Now remember, as you distribute the complement to the parentheses, the stuff inside the parentheses does not change. So we're going to have XY, that's not change. I mean, that shouldn't change. And then we're going to put the complement symbol outside of that. Or it's going to become AND. So let's put multiplication here. And then the stuff inside the second parentheses will not change. Now let's put the complement outside of that. And then the plus symbol will become multiplication. And then this is going to be W, Y, X prime, and then prime outside of that. So since we distribute the complement symbol to the parentheses on the inside, we no longer need the brackets on the outside. Now let's distribute the complement symbol to the variables inside the parentheses. So the multiplication symbol outside of it is unaffected by this complement. Only the stuff that is inside the parentheses will be affected by that complement. So X becomes X prime. The multiplication symbol between XY becomes an addition symbol, and Y changes to Y prime. Now we're going to keep this multiplication symbol. Now let's move on to the second one. Let's distribute the complement to everything inside that parentheses. So X prime becomes X, multiplication becomes addition, Y becomes Y prime, once again multiplication becomes addition, and Z becomes Z prime. So this will not change, it's on the outside. And for the last one, it's going to be W prime plus Y prime plus X. And notice that this is the exact same expression that we started with. So now you know how to use De Morgan's theorem to go from a POS expression to an SOP expression, or from an SOP expression back to a POS expression. So hopefully you understand the process of applying the complement symbol to these variables without necessarily memorizing the equations, because it could take a long time to follow the equations to get the right answer. But if you understand the process by which it works, it could be a lot easier. Now the next thing I want to talk about is some alternative symbols for NAND gates and NOR gates. So let's draw a NAND gate. Earlier in this video, we said that this is a NAND gate. So here's A, this is B, and for an AND gate, the output would be AB, but for a NAND gate, it's AB prime. Now, the alternative version of a NAND gate, you could use the OR gate symbol, but the difference is at the inputs, you need to complement it. So we're going to put a circle at the inputs. So the input is A and B, but at arriving at the circuit, A becomes A prime, B becomes B prime. Now we have the OR symbol, and so initially the output will be A prime plus a B prime. Now notice that these two are equivalent using De Morgan's theorem. AB prime is equal to A prime plus B prime. So this is a NAND gate, and this is an alternative symbol for the NAND gate because the output has the same effect. Those two are equivalent to each other. Next up, we have the NOR gate, which has a circle at the end. So given the inputs AB, the output will be A plus B. That's for the OR gate, but for the NOR gate, you need to write the complement of that. Now, another way in which we can represent the NOR gate is using the AND gate symbol, but with two circles at the inputs. So A and B becomes A prime and B prime. And using the AND operator, we are going to add, or not add, but multiply A prime and B prime. And according to De Morgan's theorem, A plus B prime, A plus B and then prime is equal to A prime B prime. And so these are two ways in which you could represent the NOR gate. This one is more common, and this is the alternative way of representing the NOR gate. Number 5, write a function given the block diagram shown below. Go ahead and try this problem. So here we have a NAND gate, and here we also have another NAND gate. So let's write the output of that. The inputs are X and Y for the first one. So the AND gate, what it does is it's going to multiply X and Y. But the NAND gate is going to do the same thing but take the complement of it. So for this one, we need to multiply X prime and Z and then take the complement of that result. Now, as the signal approaches the alternative symbol of a NAND gate, which uses the OR gate symbol, as the signal reaches the inputs, it's going to change. It's going to be the opposite of what it was. So if we take the complement of this expression, the complement of a complement basically gives us the original expression. So basically we could remove that complement symbol. So it becomes simply XY at the input. And the same is true for this one. At the input, it just becomes X prime Z. Now, using the OR operation, we can put a plus sign between these two values. And so F is going to be XY plus X prime Z. Now, how would you describe this circuit? Would you describe it as a one-level circuit, a two-level circuit, a three-level circuit, or simply just a multi-level circuit? This is considered a two-level circuit. The reason being is the maximum number of gates that the signal must pass through to go from the input to the output is 2. So let's say if the signal starts here, it has to go through the first NAND gate, and then it has to go through the second gate to get to the output. And so the maximum number of gates that it passes through is 2 gates. So this is a two-level circuit. Let's try this problem. Write a function given the block diagram shown below. So here we have an OR symbol, but this really is the alternative version of the NAND gate. So the first thing we're going to do is we're going to take the complement of these values because we see the circles at the input. So this will become X prime and Y prime will become Y. Now using the OR operation, we are going to add X prime and Y. Now what we have here is the NAND gate. And like the AND gate, we are going to multiply the two inputs first, and then we're going to take the complement of that result. So let's multiply Z by X prime plus Y, and then take the complement of that. Now at the input, we need to take the complement of this result. So basically, we just got to remove the complement symbol. So this becomes just Z times X prime plus Y. Now here we have an AND gate, so we just got to multiply the inputs. So this is going to be X prime W Z prime. Now we have the OR symbol, which is just the NAND gate as well. So what we're going to do here is add these two expressions. But before we do that, we need to change the signal because when it arrives at the input, we are going to get the complement of that signal. So the new signal is going to be X prime W z prime, prime. Now using the OR operation, we can say that f is basically the sum of those two values. So it's going to be z times x prime plus y, and then plus x prime w z prime prime. Now I'm running out of space, so I'm going to rewrite it here. So we said that was z x prime plus y, and then plus x prime w z prime prime. Now we could use the Morgan's theorem on that portion of the expression. So if you recall, a times b prime is equal to, so what we can do is we can apply the complement to the variables on the inside, and at the same time change the AND operation to an OR operation. So instead of a times b, it's going to be a plus b, but we're going to put the complement on a and b. So therefore, we can apply that here. So let's distribute the complement symbol to each variable on the inside, and let's change multiplication to addition. So it's going to be x plus w prime plus z. So we could represent f this way as well. We could say it's z times x prime plus y plus x plus w prime plus z. So now you know how to write a function given a block diagram with NAND gates and other gates. Now there's two other Boolean algebra rules that I want to go over. The next one is pretty straightforward because you can easily prove it. So here it is, a plus ab is equal to a. And the product version of that is a times a plus b is equal to a. So this is the absorption property. To prove the first one, you could factor out a, and you're going to get 1 plus b. And using the null property, 1 plus b is 1. So we can see that a is equal to a. For the second one, let's distribute a. So we're going to have a times a, and then a times b. Now, using the idempotency rule, a times a is a. Next, if we factor out an a, we're going to have 1 plus b. And using the null property, 1 plus b is 1. So a equals a. Now, the other rule that you need to know is this one. ab plus a prime c is equal to a plus c times a prime plus b. So this is very useful if you have a sum of products expression and you want to convert it to a product of sums expression. So that's another formula that you can add to your list. Let's work on this problem. Show a truth table for the following function. F is equal to ab prime plus bc prime. So this problem is not too difficult. So let's make a column for a, b, and c first. And so we have 3 inputs with 2 options, 0 or 1. So 2 to the third power is 8. So we have 8 possibilities. Now let's focus on a, b prime. First, we need to write a column for b prime. And then we can write one for a, b prime. So the complement of b, when b is 0, b prime is 1. When b is 1, b prime is 0. Now, a, b prime. So we're going to take column a and multiply it by column b prime. So 0 times 1 is 0, and 0 times 0 will be 0. 1 times 1 is 1, and 1 times 0 is 0. Now before we move on to that expression, we need to write a column for c prime and then we could write one for BC prime. So let's write the complements of column C. So when C is 0, C prime is 1. And when C is 1, C prime is 0. Now, let's multiply column B by column C prime. So here we have 0 times 1, which is 0, and then it's 0 times 0, which is 0. Next, it's 1 times 1, so that's 1, and then 1 times 0, and then it's 0 times 1, and then 0 times 0, 1 times 1, and finally 1 times 0 is 0. Now, we can write the values for f. So we need to add these two columns. 0 plus 0 is 0, 0 plus 1 is 1, 0 plus 0 is that, and then we have 1 plus 0, and then 0 plus 1, 0 plus 0. And so this is the output function given these input values. So now we know when the circuit is on and when it's off. So for instance, if A is off, B is on, and C is off, the output will be in the on state. Or if all three switches at the input are on, the output will be off. And so that's how you read this truth table. So let's say if we put switch A on and switch B and C are off, then the output will be in the on state. Number 7, write an algebraic expression for f in sum of midterm form given the truth table shown below. Show a minimum SOP expression for f using 2 terms and 3 literals. So basically, what we need to do is convert the truth table into a function. The first thing I recommend doing is writing the decimal value of the binary numbers for the inputs A, B, and C. So let's write those numbers on the left side. Here we have 0, 1, 2, 3, 4, 5, 6, and 7. Now let's identify the numbers where the function is 1. So it's 1 at 2, 4, 5, 6, and 7. So we're going to say the function f, which has the variables a, b, and c, is going to be equal to 1 when the numerical values are 2, 4, 5, 6, and 7. So now what we're going to do is we're going to write an algebraic expression for f in sum of midterm form. Now, anytime you see, let's say if A is a 0, we're going to write the complement of A. This could be for B or C as well. If anytime we see a 1, we're not going to write the complement, we're just going to write A, because we're focused on the values where the function is 1. If you write the complement of 0, you're going to get 1. So that's why 0 is associated with the complement, because we're focused on the values where the function is 1. If you already have a 1, you don't need to write the complement. So let's focus on the first part where we get a function value of 1. So that's when the inputs A, B, and C are 0, 1, 0. So notice that it's 0 for A. So should we write A prime or A? So because it's 0 for A, we're going to write A prime. Now it's 1 for B. Should we write B or B prime? Because it's 1, we're going to write B. Now it's 0 for C, so we're going to write C prime. So remember, if it's a 0, write the complement of that variable. If it's a 1, write the original variable. Now the next time we get a 1 is when the inputs are 1, 0, 0. So because we have a 1 for A, we're just going to write A. B and C are 0, so we're going to write the complements of B and C. Next, we have the inputs 1, 0, 1. So A is 1, we're going to write just A. B is 0, so let's write the complement of that, and C is 1. Next, we have 1, 1, 0. So A and B are 1. We're just going to write A and B. C is 0, so write the complement. And then the last one, everything is 1. So we're just going to write plus A, B, and C. So the expression that we have here is the sum of, we have the algebraic expression for f in sum of midterm form. Now the next thing we need to do is simplify this expression. So feel free to pause the video and using all the properties that we went over in this video, find a way to write the minimum sum of product expression of f using 2 terms and 3 literals. Now the first thing that I recommend doing is making a copy of that expression using the idempotency rule. So remember, A can be replaced with A plus A. So we're going to have f is equal to A prime, B, C prime, and then I'm going to make the copy of that and write it next to this one. Now the reason why I'm doing that, notice that these two expressions, or these two terms rather, they both have B and C prime. So I can factor that out. In the meantime, let me just rewrite what I have left over. So now I have 6 product terms. And so these are the copies, or I made a copy of this one here. Now, let's take out the GCF in the first 2 terms. So let's take out B, C prime. We'll be left with A prime plus A. And then in the next 2 terms, we can take out A, B prime, and so we'll have C prime plus C. And then in the last 2 terms, we can take out AB, giving us C prime plus C. So using the complement property, A prime plus A is 1. So we just get BC prime. C prime plus C is also 1. And so this is 1 as well. So now we have f is equal to BC prime plus AB prime plus AB. The next thing we could do is take out an A. So this is going to be BC prime plus A times B prime plus B. And we know B prime plus B is 1. So therefore, the function can be reduced to this form. It's A plus BC prime. So as we could see, we now have a function with 2 terms. So here's the first term, this is the second term, and we have 3 literals, A, B, and C prime. Now let's confirm that this answer is the right answer. And so what we're going to do is we are going to construct a truth table using those values. So let's start with A, B, and C, and then we need C prime, and we need BC prime, and then once we add A to BC prime, we'll get the function f. So let's just write A plus BC prime. So what we have in this column should match what we have here. So for ABC, it's going to be 0, 0, 0, 0, 0, 1, and you know how it goes. Now C prime, that's the complement of this column. So it's 1, 0, 1, 0, 1, 0, 1, 0. Now let's multiply B by C prime. So 0 times 1, 0 times 0, 1 times 1, 1 times 0, 0 times 1. And you can just fill out the rest. 1 times 0 is 0. Now let's add A with BC prime. So 0 plus 0 is 0, 0 plus 1 is 1, 1 plus 0 is 1, 1 plus 1 is 1, 1 plus 0 is 1. So notice that what we have in this column is exactly the same as what we have in this column. So this is the function that corresponds to this truth table. So now you know how to go from the data in the truth table to writing the function that represents that truth table. Now there's one more thing I want to talk about. Let's say if we needed to write the complement of f using this truth table. How can we go about doing it? Well, the first thing we want to do is we want to show the minterms of f prime in numeric form. Now we need to know what the numbers are. But first, let's write down the column for f prime. So when f is 0, f prime is 1. And when f is 1, f prime is 0. Now notice that f prime is 1 for the numbers 0, 1, and 3. So those numbers we're going to put here. Basically, these are the numbers that we didn't use for f. So 0, 1, and 3. Now our next step is to write an algebraic expression for f prime in sum of minterm form using the truth table. So f prime is going to be, so here's when we get a 1 for f prime. A, B, and C are all 0. So we need to write the complements of A, B, and C. Now, the next one is the inputs 0, 0, 1. That's when f prime is 1. So because A and B are 0, we're going to write the complements of A and B. C is 1, so we're going to write the original variable C. Now, the next time we get a 1 for f prime is 0, 1, 1. So A is 0, let's write the complement of A. B and C are 1, so let's write the original variables for B and C. So this is what we now have. Now, how can we simplify this expression? What I recommend doing is making a copy of this term here. So we have A prime, B prime, C prime, plus A prime, B prime, C, plus A prime, B, C, and then a copy of this one, A prime, B prime, C. Now, in these two product terms, let's factor out the GCF. So we can take out an A prime and a B prime. And so we'll be left with C prime plus C. And then in the last two terms, we can take out A prime and C. So we're going to have B plus B prime. Now, using the complementary rule for an OR operation, or you can think of addition, C prime plus C is 1. So we just get A prime B prime. So this basically disappears, and that disappears, plus A prime C. Now what we're going to do now is factor out A prime. And so we'll be left with B prime plus C. And so this is the complement of f in its simplified format. So how do we know that we have the correct answer? Well, one way is to test out that function using the truth table. The other way is to see if we can use De Morgan's theorem to get the original expression for f using what we now have. And the original expression for f that we had before in its simplified form, if you recall, is A plus BC prime. So let's use De Morgan's theorem on this expression to see if we can get that one. So let's find f prime. So this is going to be A plus BC prime, and let's take the complement of that result. Now, what I recommend doing is enclosing A and BC prime in parentheses. Now, let's distribute the complementary sign. So we're going to distribute it to A, so it's going to become A prime. The OR operation will now become an AND operation, so let's convert addition to multiplication. And now let's distribute the complementary sign to BC prime. Because we have a parentheses around BC prime, and there's two variables there, for now, let's leave it as BC prime with a complementary sign outside of that. Now our next step is to distribute this complementary sign to B and C prime. Now B and C prime are connected by means of multiplication, so that AND operation has to switch to the OR operation. Everything outside of the parentheses will be unaffected. So B will change to B prime, multiplication will become addition, C prime becomes C. And notice that the result that we have here is equivalent to this expression, which means that the answer that we got for F prime is indeed a correct answer. So that's it for this video. Hopefully it gave you a better understanding of logic gates and an introduction to logic design. Thanks again for watching, and if you really like this video, feel free to subscribe to this channel.